let's see. I thought there was supposed to be another handout with this. There is. Did you guys get a copy of this one? Yeah. You need one? Did you get one of these two?
Yeah, I have.
Okay. Yeah, so let me show the viewing audience what we got. Here's the method. Right? It looks like this. And then I have another document that helps you with the calculations. That's what this one is. All right. So a little background. What do we mean by waters of constitution and hydration? Let's start with hydration first. Waters of hydration are those waters that, let's say we have a precipitate in a chemical reaction. In other words, we put two solutions together and they react with one another and produce this solid that settles out. So we have this precipitate that settles out, and we want to filter it. So we run it through a filter and we want to dry it down. So we put it in the oven at 105 degrees Celsius because the boiling point of water is 100 degrees. So if we go in at 105, that should get rid of all the water. Okay. What we find out is that we put it in at 105 degrees, we weigh it, then we put it back in at 125 to 150 degrees, weigh it again, and the weight drops even further. So what's happened is in the crystal structure, this always happens with ionic solids. In the crystal structure of the solid, water molecules are in there attached to the ions in that lattice. And it takes more energy to get them out. So that's why we have to increase the temperature to get those out. The water that's left behind after 105 degrees drying is water of hydration. Okay. Let's see. One example is Epsom salt. You can buy it at the store. Now they say it's just magnesium sulfate, but I know it isn't. It's magnesium sulfate, and it has 7 water molecules for every formula unit. Okay, that's a lot. The only way to get rid of that is to heat it higher. This is the way we write. And I think we went over this when we were talking about naming compounds, didn't we? How to write waters of hydration. I'm pretty sure we did. You put a dot in the middle of a line, not down here, not up there, in the middle. And you say, how many moles of water are associated with 1 unit of the compound? That's what that means. Do my copy. I'll lay it down over here, didn't I? Oh, that's the first pre-lab question. No, this is Epsom. Did I say? I said Epsom, didn't I? Epsom salt. Yeah. The pre-lab question here is gypsum. Calcium sulfate can be pure, calcium, one sulfate, or it can have a certain number of moles of water attached to it. That's gypsum. And with the data that you're given here, we're supposed to figure out how many moles of water are associated with each mole of this unit. So if we do the pre-lab question, why don't we do that? Pre-lab question. Determine the value of X. So you weigh some of this compound into a crucible, and its weight before, I say mass wet. It's not really wet, but that differentiates from mass dry. The mass wet that's given here is 38.0160 grams. Okay. Then we dry it. Oh, excuse me. That's the crucible. This is plus the crucible. Okay. And this then would be plus the crucible. Yeah. The empty crucible is 33.0160. 33.0160 grams. This is the crucible weight. Okay. Massive crucible. And the dry is 36.9405. 36.9405 grams. Okay. That's the data that we were given. So what's the mass of this when it's wet? It's that one minus that, right? This is often called the tare weight. This is the container. If you subtract the container from this total, you get the mass of that wet, don't you? Okay. So where's my calculator? So if we subtract 33.0160 from that, that's 5, isn't it? Yeah, 5.0000 grams. That's the mass of the wet. Okay. Mass of the dry then would be subtract the same, because crucible is not going to change. So I'm going to have to do this one the old-fashioned way, the new-fashioned way. 33.0160. This is 3.9245. 3.9245 grams. That's dry. Okay. All right. How much water did this compound lose when we heated it from here to here? This has got water in it. This one doesn't, right? So you subtract them. Right? Subtract those two. And we get 1.0755 grams of water. And this is that water right there. Okay. We can tell how many moles that is because we know the molar mass of water. So 1.0755 grams, and convert that with the molar mass of water, 18.02, is 5.9684 times 10 to the minus 2 moles of water. Okay, so we know how many moles of water. How many moles of calcium sulfate? Do we have the mass of calcium sulfate without the water? Yeah, right here. This is the mass of calcium sulfate without the water. So if we convert that to moles of calcium sulfate, we have 3.9245 grams of calcium sulfate. And then we're going to multiply that times the molar mass of calcium sulfate. I have to calculate that one. I don't remember what that is. 40.08. 40.08. And sulfur is 3207. And 4 oxygens, which is 64. So that's 136.15. Okay. Divide that into 3.9245. And I get equals 2.8825 times 10 to the minus 2 moles of calcium sulfate. Okay. So there we have moles of calcium sulfate, moles of water. We just have to ratio them, right? If we put, this is the bigger one, put this one on top. 5.9684 times 10 to the minus 2 moles of water divided by 2.8825 times 10 to the minus 2 moles of calcium sulfate equals what? Let's see. I already got him in my calculator, so I'll just hit divide. This is 2.07 water per 1 calcium sulfate. So the nearest whole number to that is 2. That means X equals 2. Okay, that's how you find out the value of X for any compound. That's the easy one. Waters of hydration. Now for waters of constitution. That's the tricky one, and that's the main reason that I put that document together. So let's go look at waters of constitution, what that means. Let's see, the pre-lab was just waters of hydration. We don't have a pre-lab question for constitution. The difference between waters of hydration and waters of constitution is that waters of hydration have the water molecule in the formula. Waters of hydration do not. Waters of hydration, you don't even know water's there until you heat it up. And then the water comes out as a product. So the water's not there until you heat it. Right? And the one we're going to use for our example is sodium bicarbonate, or sodium hydrogen carbonate. Right? So there's your hydrogen, there's your oxygen, and when it comes out as that, and it leaves something behind. That's the trick. We got to find out, we got to reason what is it that is left behind. Okay, so that we can write a balanced equation. And you're going to go through the same steps as you do for the waters of hydration. Right? You put a known amount, you weigh your crucible, which is a little ceramic cup that can stand up to high heat. And you burn it out first, and then you let it cool down in a desiccator. Desiccator is a special device with in our case, has anhydrous calcium sulfate in the bottom that sucks up water at the ratio of 2 to 1. And it keeps that environment moisture free. So as it cools down, it doesn't condense moisture on its surface and bias our calculations. Once it's cooled to room temperature, you take it out of the desiccator and put it on the balance. You find out the mass of your crucible with the lid. And then you weigh out your wet sample, just like in either case, what we call the wet sample. And then you weigh it again. Right? And then you determine that wet weight, and you subtract the crucible from it, and that tells you how much material you have in there. Then you burn it under a Bunsen burner and drive off the water. In either case, you're driving off water, and then you stick it in your desiccator and let it cool down again, and then weigh it again. And that's it. That's all the data points you get, all the information that you get. And you have to do the calculations for the rest of it. That's why that other document. Okay. So, there are some laboratory questions here that you don't do until the end, but this is a formal lab. So your notebook needs to be set up properly, and you got a week to do it. Okay. Any questions? I didn't go into a lot of detail on this one because if I did, I'd give you all the answers before you do the experiment. I don't want to do that. That takes all the fun out of it. The procedure itself is not that difficult. It's like most experiments are simple, and what do you do with the data afterwards? That's the key. That's the trick.